So today is the first day we're going to be moving on from dApp development. So no more Solidity, no more smart contracts, no more messiness, hopefully, a lot of theory, and a lot of development in environments that you folks should be familiar with. So perhaps a lot of Python, maybe some Java here and there. We'll see. So today we're going to be talking about peer-to-peer networking. And so first of all, before diving into any more protocol stuff, we want to make sure that you guys have a good understanding of distributed systems, of what it means to run a network, how a network operates. And so that's the first thing we're going to be doing, followed by basically everything else you see on the board. Okay. So you may recall this diagram that we used in one of our first lectures. And we use it specifically with Bitcoin to describe things like consensus, things like mining, just to introduce identity and transactions and what they look like. And this is the Ethereum one as well. So what layer have we been working on for the past 2 or 3 weeks on Ethereum? Does anybody know? Application. So we're moving away from the application layer for Ethereum and basically talking about everything else. All right. Let's hold on for a second. Rewind. Let's build that mental model we were talking about first, before diving deep into all that stuff. Okay. So what is a distributed system? Has anyone had any past experience? BitTorrent. But what is it?
It's like lots of different computers all communicating information to each other.
Yeah, so distributed systems describes like a wide variety of different interoperating systems. One of the main things people refer to when they talk about distributed systems is a computer-based distributed system. And on top of that, you build P2P protocols, like things like LimeWire, like things like Gnutella, and we're going to talk about all those today. More succinctly, though, more formally, we say that distributed systems are a collection of entities, right? And this can be computers, and this can be other actors that are autonomous or programmable, asynchronous, failure-prone, and communicate through an unreliable medium. And this should already get your brains going as to what we mean by this in relation to a blockchain. Because in a sense, blockchain is also a distributed system as well. Does everything make sense so far? Okay. So let's go through some visual examples, right? What is a centralized system? Let's start with that. Blockchain at Berkeley decides to start a company, and Nadir decides to interface with that company, right? Files a GET request to pull Bitcoin.jpg from the server, from the database of that company. Simple, easy. Everybody should be familiar with how a centralized paradigm works. It's all very sequential as well, right? Different people can make different calls, and the centralized entity will respond with either failures or successes, right? And many people can do that. Most operations build themselves in such a way that they're scalable to multiple users. And scalability is another thing we'll talk about further down the line in the scope of distributed systems. Okay. So what is the issue, right? What is the problem with a centralized entity, though? Central point of failure. Is there something you would?
The centralized entity could like corrupt something.
Sure. Yeah. Yeah. It has the power to manipulate the data, right? So, in this class, we want to move away from centralized entities. Okay. So let's take on a P2P example, right? And so now Bab Inc. acts as an intermediary, right, between multiple other nodes. An example of this might be something like Napster. Who's familiar with Napster? Can somebody describe what they did? Or what their original mission was?
Like free music and audio.
Okay. Make available, give a platform for people to share their music and audio files. Anybody else? What is a P2P system? A P2P network. What does P2P stand for? Peer-to-peer. Right? And so the way Bab works now is that it facilitates, say Nadir wants to look for Bitcoin.jpg. Napster realizes that Aparna has Bitcoin.jpg, files a GET request from Aparna, gets it back, and returns it to Nadir. Very, very simple. Does everybody see how we've shifted away from centralized entity? Okay, so what's the benefit of this model? Over the first one, or just in general?
The data is not stored inside the centralized.
Exactly. Napster or Blockchain or Berkeley Inc., they're not storing the data. The data is hosted in a decentralized manner. Okay, so that alleviates the concern of the person at the back who gave that answer, right? Now, what was the other answer we heard? What was the other issue with centralized entities?
Central point of failure.
Again, does this fix the central point of failure issue? No. Right? So many people can interact with it, but again, still a central point of failure. And in fact, what ended up happening to Napster? It got shut down. Right? Why did it get shut down?
Facilitating copyright violation.
Right, copyright violation. It got hit by Metallica first, I believe, and then Dr. Dre, and then got hit with a little, fee of $10,000 per download. Of course, nobody can keep that afloat. So, central point of failure. Let's focus now on a better P2P system. What does a better P2P system look like before we dive in? No central point of failure. What's a huge example of a decentralized P2P system that we've been talking about in this class? In fact, it's the very foundation of what this class was built on. Blockchain, right? So, when I ask that question, I should hear you resounding blockchain, because blockchain is the better P2P system here. But there are other models, right? Blockchain isn't the only one in the space. So how does this model work? You have 5 peers on a network, and each of them have this table of known peers, right? So Nadir, again, we are first person Nadir throughout this whole lecture, right? So Nadir has this list of Gloria, Parna, Max, and Philip, and where to find them. And if he wants to get a file, if he wants to look for a file, he doesn't need to go through any centralized entity, right? Just ask him directly. Fantastic, right? Problem solved. Who thinks problem solved? Who thinks problem not solved? 2 people in front. Everybody else thinks it's in superposition. So 2 people in front, you guys are right. It hasn't been solved, right? So let's run through it. Nadir is still looking for a picture of a Bitcoin, right? A Bitcoin.jpg. He makes the query to Max. What happened? So maybe on day 0, Nadir got the list. Nadir makes a query on day 20. Max is no longer at that address, right? There's nobody at that address. That node just disappeared, right? And because you're an asynchronous, decentralized system that works in this way, you have no way of knowing where your other peers are at in the interim, because this is the only list you have to go off of. What are some improvements we can make to this? Make it so that you can go to anybody? Okay, cool. Mm-hmm. So basically, store a hash table somewhere, right, of available data. And actually now we're starting to see more and more that we're building towards this image of a blockchain, right? Because with blockchains we store this like immutable ledger, right? And everybody will have to store it, right? One thing leads to another. You can see the inferences we're making and where we're going. And so blockchain is obviously the natural conclusion here, or one of the natural conclusions. But there are many more that we can cover. And in fact, we are going to cover a viable alternative to blockchain in a few slides. What are some other improvements? Just to this. No need to think ahead. So we could query more often, right? Instead of querying on day 20, we don't have to query for Bitcoin.jpg, but we can say, hey Max, on day 1, are you up still? Yeah, he's up. Day 2, Max, are you up? Yeah, he's up. Day 3, Max, are you up? Yeah, I'm up. Day 4, Max is down, so I know not to waste my time on day 20 looking to Max for Bitcoin.jpg. Does that make sense? Awesome. All right. So poor Nadir, still looking for Bitcoin.jpg, still doesn't find it. Okay. Different model. Take 2. What is an MST? Minimum spanning tree. What is a minimum spanning tree? Yeah, so it's a way of connecting the entire graph. By the way, for people who haven't taken CS70, a graph is basically what this is. It's a representation of nodes through nodes and edges. Excuse me, it's a representation of networks, right? Through nodes and edges, where edges are the lines between the nodes. And instead of connecting everybody to everybody else, what we're doing here is we're drawing the minimum amount of lines between nodes such that everybody can reach everybody else. So basically, Nadir can reach Philip by going through Gloria, Max, and Aparna. Does that make sense? Awesome. Okay, and actually, there's only logarithmic overhead with network growth. Is that a good thing or a bad thing? Really good. Okay. Why is it really good?
Because when you get really big size.
Yeah. So think about having to connect a peer to everybody else every single time a new peer joined the network. That is so much overhead. So you need to connect a new person. They need to be connected to Max, Nadir, Gloria, Aparna, and Philip. Then the next new person needs to be connected to all those people plus the first new person, and so on and so forth. But here you only make basically a couple of connections every time a new person joins. Just enough to maintain this minimum spanning tree. Okay. Perfect. We found our peer-to-peer network, right? That's it. Problem solved. Who thinks yes? And I want to see everybody's hands go up this time, right? Who thinks no? All right, thanks.
All right, thanks.
So what's the issue here?
What's the issue here?
Okay, latency is an issue. Okay.
Okay.
Uh-huh. So Nadir, is that more question marks than there were before? Maybe. I don't know. He's like really persistent, right? He's trying to get this Bitcoin.jpg. So, naturally, who does he ask? Gloria. Okay. He asks Gloria. Makes a query. Right? Gloria doesn't have it. She queries Max. Now this is day 20. What happened to Max? Okay. That's not a problem, but we need to reroute right now. If he goes down. If it is the case that on day 20 he goes down, we need to like reconfigure this entire network. We now need to make sure Gloria is hooked up to Aparna. And depending on the scheme you use, that can be very efficient or very bad. Okay. But something else could happen, right? There could be a lossy channel, right? And because Gloria is only making that query to Max and nobody else, it could be the case that she has to send the data packets multiple times due to corruption, due to just it being dropped. That's obviously bad, right? Now, what makes it worse is that Max, if he's online, may not even ever know that he's being sent packets. And so what is the exact issue here? The issue is that using an MST model forces us to connect to only one peer. So what is the, where am I going with this? I'll give you a clue. It has to do with the word propagation. Okay, it has to do with the word broadcast. Exactly. So instead of Gloria just talking to Max, why doesn't she talk to everyone around her? And maybe one of those people will be able to find the answer. Right? Okay. One caveat though, this is generally a good model for networks that are neither lossy nor require a lot of like continual maintenance in the short term. So like cell towers or like anything wired or fixed infrastructure, this model is fine for generally. Okay. So speaking of broadcasting, that leads us to the gossip protocol, right? And so we've already discussed why things like being failure prone need to lead us to make smart choices about our network. We've already talked about why communicating through an unreliable medium, right, need to make us reconsider, right, if you're communicating through lossy networks. But we haven't really talked about autonomy or asynchronousness. So let's look at that right now. Nadir can send messages, right? There he is on the right. He can send and receive messages, 1 and 0. And that is basically autonomy. He can choose to set up a script running on a certain port that manages outgoing and incoming packets. Now, what's the problem with that? The problem is that things don't happen sequentially in a distributed system, right? As we've talked about, going back to the definition. Things happen in an asynchronous way. And so when I'm handling sending a message and another message is coming my way, I can't really handle the message that's coming my way, right? Or if two messages arrive at the same time, that's an issue. So how do I handle this asynchronous paradigm that I'm working within? So I have an inflow and an outflow. Two buffers that just store those those packets until I can get to them. Until I can either send them out or bring them in. Okay. So speaking of Gossip Protocol, after the death of Napster, people started collaborating and came about and like started building this open source network called Nutella. She's silent. And then the way it will work is you would join the network. Okay. So Nadir gets this promise of a great P2P network. He joins it. He downloads the client and everything on his computer. And on the client, there are some cached addresses that tell him, hey, these are two nodes you can connect to. Aparna and Gloria. Right? So Nadir connects to both of them. He pings them, right? And then the response he gets back is a Pong. So this is what's called network discovery. This is how you, as somebody new to the network, can be onboarded. And Akash will talk a little bit about how that works specifically in the context of Ethereum a little bit later on. All right. So, okay. Nadir is on the network. He is connected to at least two nodes, right? Aparna and Gloria. And so he makes this query, right? Bitcoin.jpg. And he sends it out. And Gloria is connected to 0 peers. So the query dies there. But Aparna is connected to 2 other people. So the query continues. And in fact, at long last, there's a query hit. Right? At Philip. So Philip had it all along. And so Philip returns it to Aparna, and that's returned to Nadir. Who's taking a networking class? Wow. Cool. So there are a few protocols underlying the internet. IP, TCP, and UDP, to name a few. And we'll go over those in a little bit. But what is significant about this is that it is facilitating the transfer through nodes. Right? You're saying, okay, you're asking for this data, but I can't send it directly to you. I'm going to send it through somebody else. I hope that's okay. And in a lot of cases, this data was unencrypted. It was open. And in a sense, especially in the early days of things like LimeWire, nobody minded because you were just transferring music, right? You're just transferring movies. Okay, cool. So there is one more paradigm in Nutella, and that's the push paradigm. And this was used specifically to send data directly between nodes. And this was used in the context of things like firewalls and other niche use cases. Okay. So we've talked about autonomy and asynchrony. And this is, I guess, how it would work. And so a little bit about the protocols. So you guys haven't taken a networking class, but are you familiar with either TCP or UDP? Can anybody explain the difference? Right. So TCP is a secure method of sending packets. You can be assured that if you send data through TCP, they'll arrive at the correct destination. Whereas UDP is a quick and dirty way of doing things. And if it fails, as you mentioned, that's it. Sorry, bud. Now, what is IP? And HTTP, and how does that play into this? Which one? IP. Okay. Exactly. So, a good analogy for this that ties all of these together actually is think of like a highway, right? IP is the highway, or the neighborhood, or the location, whatever you want to think about it as. TCP and UDP are the transport protocols, so you can think of them as trucks. Right? And HTTP is actually the payload that the trucks are carrying. A more recent development is HTTPS. Does anybody know the difference between HTTP and PS? Yeah, it's SSL secure, right? It's SSL encrypted. So basically, always use HTTPS on your websites. There's no reason not to. And actually, Nutella has used TCP in conjunction with HTTP and IP, of course. And only more recently, in later releases, has started incorporating UDP into it. Okay, so let's talk a little bit about network faults and the things you got to look out for. So, what are the two types of faults? A fail stop, or crash failure. And there's like a little bit of nuance into like how you choose to talk about this, but the overarching kind of like definition is a performance failure, which is like a slowing down of an output. So you received the output from a node in a slower time than you expected. And that gets worse and worse and worse until you get to a fail stop, where you know that the node is down. And then you have a Byzantine failure, right? Does anyone want to describe it in their own words? Does anybody know what a Byzantine failure is? So, there you go. Yeah. Yeah, exactly. So you're touching on the Byzantine generals problem, which occurs as a result of Byzantine failures. And so what Byzantine failures are is everything else. Every other failure that you can envision happening on a network by a node is a Byzantine failure. So instead of just shutting off or not responding, a Byzantine node may send the wrong answer that is not in line with what the protocol requires. So you send a Byzantine node a 1, they'll send you back a 0, even though the protocol requires that they send back a 1 as well. And so before we move forward, I just wanted to make a note of this paper. It's very, very interesting paper. It talks about how you think about asynchrony in terms of systems, because you can't really rely on real time to gauge what happens first and what happens second. Because if you take the board, if you're running 3 different processes, one process may not know that certain events have occurred until after an event is transmitted. And the dotted lines actually highlight the landscapes and the contexts in which certain events can be seen by other processes and when they can't. Anyway, take a look at that paper. It makes reference to logic clocks which is a way of kind of consolidating this idea of asynchrony and being able to say what came before what in terms of network events. And there are three key components, I guess, that describe Byzantine fault tolerance. Two of which are kind of grouped together into this correctness pairing. So one of them is safety, right? And that means that results should be valid and identical at every node. Right? And the other one is liveness. So nodes should be available to query, basically. Right? In some non-infinite time. And then, of course, you have fault tolerance. And so, the FLP impossibility is this notion that you can't have all three. Or rather, that you can't have correctness 100% and also remain fault tolerant. There's also a separate theorem that came out sometime in 2000 that describes sort of a similar issue with regards to distributed data storage. And the real takeaway here isn't just that you can only pick like 2 out of 3 or 1 out of 3 of these things. It's really that if you're in an environment that is not partition tolerant, as many networks are, then you really have to make a trade-off, right, between the first two things, consistency and availability. Can anybody think of an example of having a distributed storage system and having a partition within the system, which means that basically due to some network switch failure, the network kind of splits into 2 partitions, nodes A, B, and then on the other side C, D. Say you want to send $100 to the network, right? What happens then? Does anybody want to guess? So say you send $100 to the network that is now partitioned. Okay. So it'll lead to 2 conflicting versions.
Yeah, or you could like shut down one or the other.
Yeah. So say you update both of them at some point, then the network partitions, and then you push an update to the other one, right? And then that goes down. The latter one, right, goes down. So if you're prioritizing availability, then your system will return to you an answer that is old, right? Because the one that is not down is obviously available. And if you're looking for consistency, right, the correct amount, then your network, your protocol will complain to you because it knows that the one that is up, right, is not the correct answer. So this is a very, very basic overview of the way of what cap theory describes. But yeah, speaking of simple, I thought it might be fun to explore the FLP paper a little bit. So again, the FLP possibility result, right, has a few lemmas that it brings up. And lemma 2 specifically is this, right? There's some initial configuration in which the decision is not predetermined, but in fact arrived as a result of the sequence of steps taken and the occurrence of any failure. What it means basically is that the observation that you make of a network is non-deterministic. You can't determine beforehand, basically. And so the proof for that is that you can say assume all initial configurations have predetermined executions, right? So you have a network with two nodes, right? Where node A is 0 and B is 1. Or actually, what is every combination of nodes we can have? Okay. Good. Exactly. Okay, and so we've chained them together in such an order that basically, if you start with 1, 1, okay. Slight mistake. But the important thing here is to look at these two. So this part is correct. And what you're looking at is two configurations, right? That are one different than the other. So 0, 1 is different than 0, 0 with a difference of 1. Does anybody not understand what I mean with a difference of 1? Okay, good. So you have configuration C0 and C1, right? And we're saying that for any situation where we have these configurations, the predetermined output is going to be 1 and 0 respectively, just arbitrarily chosen for our system. Okay, what if it goes down? What if B goes down right now? How does that affect our system? So we say for C0, with the configuration that we had, if B goes down, then we have an output of 1. Right? But then we say for C1, which has the same predetermined execution, basically, we say that that has an output of 0. And so that's a contradiction, and for those of you who haven't taken CS70, that's fine. This basically contradicts the claim we made, which proves the lemma that we originally talked about. Is anybody confused by that? Mm-hmm.
Like in this case, it's like a 4. Like in this case,
Yeah. We could have chosen for it to be anything because we designed the protocol.
It's about like predetermined like initial configuration versus like the initial configuration versus like the. I guess like if you change the initial conditions, of course the resulting
So if you change the result,
deterministic, it means like the initial configuration doesn't affect the
yeah, exactly. But we're seeing here that it does. So it's wrong. Exactly. So you got it. So basically, the mistake that this assumption makes is that it says even with faults, whether they're Byzantine or otherwise, this holds. But in fact, the claim that the lemma is making is that if you introduce faults and asynchrony into the system, then you have this contradiction. And this, of course, doesn't prove the entirety of FLP impossibility. I suggest you look at lemma 3, which is much more, I would say, intense, but still very interesting. Okay. So finally, let's talk about Eclipse attacks. I felt like a lighting change. What are Eclipse attacks? Who's good with security? Nobody is good with security. That's fine.
Is this the thing where you like? That's fine. Is this the thing where you like one person connecting like two different groups and then like knock out that two different groups? One person on there, and one person.
Close. I see where you're going with this. Yeah. So that specific one can be done in many ways. So Hamdi said that basically you partition the network as the attacker to isolate a victim, and you man in the middle their responses such that they believe they're interacting with the real network. But that's just one type of Eclipse attack. This happened in 2016. Border Gateway Protocol hijacking. So the Border Gateway Protocol isn't that important. It's meant for automated systems, usually across long distances. But what ended up happening here is that they were sending a data packet from Guadalajara to Washington. Should be pretty simple. But if you look at the map on your left, you'll notice that it goes all the way to Minsk, Belarus, before going back to Washington D.C. And actually, the company that plotted these doesn't have a clear idea for how they happened. The responses that they get from foreign ISPs are, there was a bug. It's been patched. So this specific attack, you see another example on the right, isn't blockchain specific. But in 2016, somebody used the Border Gateway Protocol hijacking to orchestrate an Ethereum specific attack. And so it's in that way that this is considered an Eclipse attack. And so the more well-known Eclipse attacks, and there is like some, contention as to whether civil attacks are Eclipse attacks, or Eclipse attacks are civil attacks, or they're completely different. But definitely a civil attack is one way of carrying out an Eclipse attack. And so we have the network from before, with Nadir querying Aparna and Gloria, and then Aparna querying Max and Philip. Okay, all well and good. But what if Nadir has been querying Oski this whole time? What if Oski has made like multiple identities on the network? So let's backtrack a little bit. A native civil attack, a vanilla civil attack, is an attack on a reputation system where you're in an anonymous environment and can basically create infinite identities in order to vouch for yourself. And so you can see here how the notion of multiple identities carries over into this Eclipse attack. And so once they set themselves up in this way, they can basically interact with Nadir and feed him false information and even cause a double spend attack. So in this case, they're sending back a Bitcoin.jpg, just a fake version of the original data. And Nadir has no way of knowing unless he manages to interact with some outside peer. So these are the list of nasty things someone could do if they carried out a civil attack. Lastly, we have time attacks. And time attacks are actually very, very simple. If an attacker can get their hands on your system clock, if they can set it a little bit more than 20 seconds past actual time, the network will ignore you. And if the attacker sets their system time to the same system time as you have, they can connect to you. Or you can connect, you will interact with them as if they were the network. Okay. Cool. So at that point, I'll hand it off to Akash. No, you can use that mic. Or should I just make sure it doesn't. Let me just get it done.
Okay, cool. I'm going to be talking more about protocol related stuff to Ethereum, and also just like the general field of peer-to-peer protocols. I think it's very important to know. So we talked about Napster. It relied on a centralized database, and that was like the first generation of peer-to-peer file sharing networks. Then we had the second generation, which was Nutella, and that would use flooding to locate files. And they basically search every node on the network, so it wasn't quite as efficient. And then the third generation ones that I'm going to kind of talk about is distributed hash tables. And this is a very convenient way to look up files on your network. And you can also store different resource locations throughout the network on different nodes. So not every node therefore has to store every single mapping to each file, right? So you can see like the gradual increase in efficiency and redundancy that's like happened. Yeah, so basically Napster, you'd have to, when you joined it, you would basically have to send a list of files that you held on your computer, and the server would be able to perform searches for those files, and it would refer any queries that it received to those nodes that were holding those files. So there's just this like centralized server that was keeping track of all the mapping of all the files on the network, and it was a great way to like share like music. This was vulnerable to all kinds of attacks and lawsuits. Like somebody could just DDoS the Napster server if they really wanted to, and lawsuits because if they had it was a company and they just had like a centralized service, and the company is still active today. It's owned by some subsidiary called Rhapsody, which runs like a music service. But yeah, they completely like pivoted from like what they used to do. But yeah, this motivated the whole need to do more research on this type of stuff. So there was a lot of like foundational papers in 2001 about distributed hash tables, and yeah, 2002, and yeah, those are the main 2 years. So distributed hash table is basically, it's a hash table, right? So it has key value pairs, but the difference is that it assigns keys to different computers, which are the nodes in the network. And the nodes are going to store all values for whatever keys it's responsible for. And the protocol that you use for your distributed hash table, there's many different kinds, but they will specify how the keys are assigned to the nodes in your network. So some of the original ones that were invented in like 2001, I think Cord actually came out of like a bunch of Berkeley like professors like Scott Schenker and Sylvia Ratnasamy and some others. But yeah, the other ones are also pretty famous. Definitely recommend checking out if you're interested in that stuff. But yeah, this is like a really like simple overview. Like, so you hash your data, you get a key, and then on your network you have files stored across different nodes, and the lookup happens also like through those different nodes. So you might be wondering, like, how do we like find what files are where, and we'll kind of talk about that. But some of the properties of distributed hash tables are the nodes collectively form the system without coordination. So there's like the sense of autonomy and decentralization that's there, but we'll see why that isn't always the case. It's not ideal decentralization because of the nature of the internet. These systems are often fault tolerant. So the system it should be reliable if there's a bunch of nodes continuously leaving, joining, failing. And the system should function differently when it comes to having more and more nodes. It should be able to scale with like size constraints. If you like store things in like trees and you have to like figure out how to get the files, right? Because if you can imagine it can be pretty hard to just jump between different nodes and try to figure out which files are stored where, right? So someone has to like store shortcuts on their end in order to make this like a faster process. So DHTs also need to deal with a lot of stuff that's just dealt with in distributed systems in general. So that includes like load balancing, data integrity, performance. Obviously, one of the major like criterions is so that you can locate your files quickly, and this usually happens in O of log n time. And any kind of DHT that is designed to have BFT is able to defend like a Sybil attack. So one thing I'd like to talk about is BitTorrent, because BitTorrent does share a lot of similarities with how Bitcoin does networking, and same with Ethereum. But basically Bitcoin has a bunch of clients, and it also does have servers, but mostly clients, and the clients download parts of the files while they upload other portions of the network based on their own fairness algorithm. How many of you have like downloaded torrents before? Okay. You guys remember like what seeding and like leeching and what all that is, like peers? Yeah. So within these algorithms, there's ways that peer optimization occurs, such that most people get the best outcome, and sharing happens in an effective and efficient way. So you might notice, like, if you try to constrain your speed on one of your Bitcoin clients, like when you're for upload speed, because often when you're downloading, they also expect you to upload to like other peers that need like certain portions of that file, so that it's kind of like a shared, like fair like way of doing so. If you like try to throttle like your upload speed, so that you don't want to like be, you don't want to be like convicted of like participating in piracy, right? Like you don't want to be an uploader. Being a downloader is okay because nobody can like really prove that you kind of were downloading stuff, but being an uploader, yeah, you're fucked. So you might do that, right? So if you do that, BitTorrent, like the other clients on the network, will see that, and they'll basically like throttle your speed. So the goal is that we need to match up with other peers, do uploads and downloads based on the file we want, and we find peers through this process called Bootstrapping, and this is done via multiple DHT nodes that are in the network. And you might be wondering, is it decentralized? How do you really start a network, right? Because a network always starts off with like a few participants, and the truth is that it really isn't decentralized when everybody like starts off making all the connections. And also the internet is very unicast in nature, right? A lot of people, just because like you're connected to the web, doesn't mean you announce your whole presence to like the other billion people that are on there. So you can imagine like if the internet was like broadcast, where like everybody like alerted each other of their presence, it would be a mess, right? So your ISP and the destinations you connect to, they're the only ones who really know you're online. And multicast is, this happens when your computer is basically connected to every other computer in the same subnetwork. But again, this is not what happens in the actual internet. So because this is not what happens in the actual internet, DHT really isn't decentralized. You need to hit up a single DHT at some point in time to find other peers, and there's always some metadata that you need to have encoded in your client such that you find those DHTs. Because you can't just like scour the internet, like pinging random IP addresses, hoping that they're DHTs. Right? That's never going to work. So because things are unicast, you have to have like those hard-coded like data points, and this goes for Ethereum as well. Like when you're starting to look for like providers to like give you like the blockchain data when you run Geth. So the bootstrapping process is like this. You connect to a set of DHTs. It's usually something like router.bittorrent.com or router.utorrent.com on this specific port 66881. And these don't have to be in tandem about like what files are stored where. They can actually have like differentiating opinions about the DHT. So there's actually like no like direct consensus, but they can still communicate with each other on what files might be stored where. And I'll kind of walk you through like what that looks like. So once you like query the DHT, that DHT will send out a handful of peer IP addresses that you'll connect to, and you then connect to those other peers that have the same torrent file, and your peer list will eventually populate with a bunch of people that are downloading and uploading the same file. So the benefit here is that you can also like query, when this happens, like you can also query other people's peer lists to populate your own peer list, so you don't necessarily have to go through the DHT to populate your entire like peer list, because the DHT doesn't always have like each and every peer, but the other peers are often they often store like most of the peers because they're downloading the file. So it's like a much more effective way to just query the other peers in the network for that list. So let's walk through this. So we have client A, and it's on this weird torrent info hash, and it's basically asking the set of DHTs. Have you heard of anybody else on that one? And it gives it its IP address and port number. Then the corresponding DHTs decide to broadcast. Well, actually, the single DHP broadcasts to the other DHTs that it knows of. And if there's no info hash within the current scope of DHTs, those other DHTs that were queried will also query their neighboring DHTs, the ones that they know about, because the DHT that we originally sent it to, they don't know all the DHTs in the network. But the other ones know more DHTs and so on and so on. Like, because if everybody knew each DHT, it would have to be extremely coordinated, and it's actually kind of hard to coordinate that. There has to be like some kind of consensus, and there is no like consensus in BitTorrent. So you're successful. One of the DHT ends up finding that client B is currently working on the torrent via the info hash you sent, and then client A is made aware of client B from the DHT, and then client A reaches out to client B, and they do a handshake and they start some kind of file exchange. And this is like a pretty simplified overview, but I think this sets like the grounds for what we're going to eventually talk about. So one of the issues is that client A can't really quite yet contribute to client B and C. But what if client B gives them more data such that they can? And then more connections end up being formed between like client A and the rest of the clients. Then basically, then peer-to-peer file sharing ends up working quite well. You can see like the network is much more connected. There's much more file sharing going on, and this will result in like faster like overall transfer of files to everyone. So later on, we're going to talk about like IPFS and Swarm as like peer-to-peer networks, but what I'd like to keep talking about is more on the Ethereum side of peer-to-peer communication, and this actually isn't a very well documented thing for Ethereum, but I think it's really important to go over. Yeah.
How effective are the type of attacks where, like, say, you want to disrupt the network? How effective are, like, pretend to be like a client is trying, but like sharing false information? Pretend to be like a client and trying, but like sharing files.
Good question. So it really depends on like what kind of files you're like uploading and downloading. Sure. If it's not like a very like popular like file, like what would the attack be? I guess in your case.
If you're becoming that host, you don't want people streaming.
Ah.
So you're not becoming that host, things that are going to
I see. So so BitTorrent actually like does a checksum of what it's downloading. So not in terms of like partial packets, because the partial packets aren't malicious because things aren't being executed on your machine. But once like the complete picture is downloaded, there's a checksum that gets generated, and then that checksum is checked for, and then it knows like, oh, this is what I have, and it's verified with like the rest of the network. Yeah. In order to thwart that, you'd have to essentially thwart the people that have downloaded like 100% of the file and are just like mostly seeding, and then you'd have to take the majority of that. Yeah. So we kind of talked about what an enode URL looks like, but I'd like to recap for you guys. So an enode basically is this really long URL. It looks a little intimidating, but all it is like you specify the enode protocol. You then have a hexadecimal node ID right after it, which is pretty long. And then afterwards, you put an @ sign, and then you have the host name, which is an IP address. Then you have the port, which is the TCP like listening port. And then you have the, it as an optional parameter, you can also specify the discovery port if it's different. And you'll see why TCP and UDP are like have different ports and are being used in the context of Ethereum nodes here. So we have, this is kind of like an overview of how enode selection essentially works when you're looking to bootstrap on the network with like a current geth node. So this would be an example of, say, I run geth on my computer. It's trying to find other nodes and sync up with other people. So I have my geth node on the left, and I also have my DHT, which contains a public key using elliptic curve key generation, and then it has an enode like value. So this is like the lookup table, and essentially my node is going to query the DHT, which is actually hard-coded into Ethereum clients, and try to find an appropriate enode to go to bootstrap and download portions of the blockchain. So this is actually a randomized process. It actually just goes through nodes randomly, and then so in this case we'll select the second one. And then once we select an enode, we actually reach out to that enode using TCP. We try to establish the connection, and we establish that the other node will, this enode will like acknowledge that that it's available and ready to receive. Then these two basically start to exchange data. So geth node 1 will send what kind of Ethereum I guess APIs it supports, or what kind of Ethereum like versions it supports, and then the same will happen for the other enode, and they'll basically come to an agreement on like whether or not they can work with each other, because not all Ethereum nodes can work with each other in the network if they don't have the same like protocol version. So this supports ETH62, and this supports ETH63. However, this one supports ETH63 only. But because there's a match, they're compatible. So it's a valid enode to go to receive blockchain data. So now there's the blockchain info exchange. Basically, it starts by sending off like a network ID, which would specify like mainnet, Ropsten, Rinkeby, whatever like network you're using, and it'll send like the Genesis block to like see if you guys are using like the same like chain. And this is a case where like if you don't find a match, then you basically have to like start the search again for like another enode, and that means you have to go back to DHT, and that means you have to go find another enode. So you can see this kind of like inefficient, right? Like this is actually like a really bad inefficiency, because you can imagine like if Ethereum has some kind of a hard fork and the whole updates are not like coordinated very well, and version nodes start like the versions start to get off, and there's no like backwards compatibility. Usually it's backwards compatible, so that's why like stuff ends up working out. Then you literally have to just keep searching through the DHT until you find a peer, and that's like kind of dumb. There must be like a quick way to do it, right? So one thing to note about DevP2P is that all Ethereum clients have to comply with it. It is essentially the wire transport protocol for Ethereum. And if you can't speak the same language as other clients, you can't really participate in like the whole, I guess, scenarios they're working in, right? So DevP2P uses something called ROPX, and it's basically just an encrypted and authenticated transport protocol that's under DevP2P, whereas DevP2P is more of just like the name for the Ethereum client spec. So you can think of them as kind of the same thing. They're very synonymously used. And ROPX actually uses something known as Kademlia as like the routing mechanism, and this is actually a peer-to-peer like distributed hash table. It's responsible for node discovery, as we saw before with the distributed hash table we had, network formation, and also having multiple protocols over a single connection. So I think it's important to dive a little bit into Kademlia and talk about how this, I guess, peer-to-peer info system works. So Kademlia is basically a peer-to-peer distributed hash system that lets us find other nodes in the network to work with. And there's basically configuration. So there's a few cool properties of this, actually. One is that configuration information will spread automatically as a side effect of the key lookups that you perform on this whole network. So that's like you're doing two things at once, so that'll greatly improve performance. Nodes have enough knowledge to route queries through low latency paths. So oftentimes whenever you're trying to find a certain, I guess, key, you will basically be converging in log n time. So it's usually very efficient based on latency because of the data structures we use. And I'll kind of talk about those. It uses parallel async queries to avoid timeout delays from failed nodes. So that way you just don't like stop just because like somebody like fails. You just keep on querying until shit works. And then when searching for any kind of value, the algorithm will essentially find nodes such that it'll converge on the key. It'll get closer and closer each time. It does like it looks for the key. So that's why it's like log n in terms of search. So let's dive a little bit into the whole structure. So nodes have 160-bit IDs, and we want a lookup algorithm that locates successively closer nodes to any desired ID, and we want it to converge to the lookup target in logarithmic steps. So key value pairs are stored on nodes with IDs close to the node for some notion of closeness, and this can be latency related, or you could come up with other parameters, but it's kind of up to you to decide how you want to implement this. But the protocol will treat nodes as leaves in a binary tree, where each node's position is going to be determined by the shortest unique prefix of its ID. So you can see here, all the nodes are actually at the bottom of the tree. And this is like a prefix tree. So the protocol ensures that every node knows there's at least one node in each of the subtrees. And what are the subtrees? So let's walk through an example. So let's take a look at the node with prefix 0011, and we want to divide the tree into a series of subtrees that don't contain that node. So if we look here, the highest subtree will contain half the binary tree that doesn't contain the node, and the next subtree consists of half of the remaining tree not containing the node, and so forth. So it actually doesn't show the other nodes that I'd be like essentially looking up to converge, but there'll be another diagram that shows it off better. But this is basically how things converge. Each time we find that like half subtree that wasn't quite there, and in this case it's going to be this bigger picture one. But in these cases, it's going to be so it goes step 1, and then the other like subtree is going to be step 2. So that's the other subtree that was neighboring it, and this kind of just like runs recursively, if that makes sense. So this is how we kind of like closely converge to like nodes each time. It's through that recursive algorithm. Does that like make sense? Do you want me to walk through it again? Okay, so I'll walk through it again with this example, with this diagram, and I'll go a little slow. But you can see here that this is the space of the 160-bit numbers, so this actually might make it a little easier to understand. But say like we're trying to find, we're essentially trying to converge on prefix 1110, and we have, we start at, our node is 0011, so we start at 0011. We would then realize that the subtree for that is going to be this little guy here, and the subtree property will point to this node here, which is 101, and then that'll like begin the search for the next node, which will be in the next subtree, and so on and so forth. And eventually we'll converge on 1110. So why exactly does this work, and like what are some other properties of this tree? So nodes basically have 160-bit IDs for themselves, and so do keys. Keys also have these 160-bit IDs, and because Kademlia actually relies on the distance between two IDs, we can define this distance as the XOR of the like the key and the value, or sorry, not the key and the value, but the node ID and the key, where like the key could be X and the node would be Y. So we would simply XOR it. And why does XORing the key and the node ID work? So let's say we have a fully populated binary tree of 160-bit IDs, and the magnitude of the distance between those IDs is the height of the smallest subtree containing them both. When a tree is not fully populated, the closest leaf to an ID X is a leaf whose ID shares the longest common prefix of X. So here we like look for the longest common prefix of the IDs, and like that's how we ended up converging to them. And the edge cases are if they're like empty branches. There might be more than one leaf with the LCP, and in that case, the closest leaf to X will end up being produced by flipping the bits corresponding to the empty branches in that tree. So let's say there's like an empty branch. The closest leaf, for if you needed to converge, might require you to just flip the bit. So one thing with transport is that when dev P2P nodes end up communicating, they use TCP. UDP is only used for when you query the distributed hash table to get information about eNodes, but you need TCP in order to you need TCP in order to basically communicate between the two nodes to like transfer data and make sure it's reliable. But on top of that, we have something called RLPX, and that allows the sending and receiving of packets. And packets are dynamically framed. They use something called RLP encoding, and they're encrypted and authenticated. And multiplexing ends up being it ends up occurring because we have the frame header, which specifies the destination protocol of the packet. So you may want to think about how packets can be received asynchronously via multiplexing. You can think about like combining the asynchronous aspect of UDP with the reliability of TCP. And this is actually RLP, but let me move to multiplexing. So multiplexing is like how we do that like combination of like UDP's like speed and like TCP's reliability. Basically, you divide your channel into an arbitrary number of variable bit rates or data streams, and then each stream is then divided into packets that are normally delivered asynchronously in an FCFS fashion, first come, first serve. So packets may be also delivered according to some kind of scheduling. You might have some queuing. You might have quality of service to prioritize other people, which is bad for net neutrality. But this also implies on-demand service rather than the one that pre-allocates resources. So we don't try to pre-allocate for multiplexing purposes. We try to do things on demand to maximize the speed between like all the packet transfers we do. I also mentioned RLP encoding. I think this is pretty important to understand how data gets serialized in the network. Like this happens not only with the transfer of data packets, but it also happens within the Merkle trie structure. So yeah, the purpose of this is to encode structure such that it's easy to just send. And an example of this, it's actually not as bad as it looks. If you want to RLP encode the string dog, you're simply going to start off with the byte value x80 and the length of the string. So that ends up being 3. So you have this 0x83, and then you put in, you basically just serialize dog by just splitting it up into individual characters. And you can do the same for a list, except the only parameter that you need to change is that along with the byte value for like the length of the string, you also need to include the byte value for the length of the list. So in this case, it was the length of the list ends up being 8 in this case. And the reason is because we have the size and we have this string data, and we have the size and the string data again, and that adds up to 8. So then we have 0xC8, and then this is 3, and then this is 3, and then we send 3 and 3. So it's actually like very, very easy. Yeah, so with the transport protocol, yeah, good question. We'll talk about that with the Merkle Patricia trie implementation, because that's actually like an issue, but it's a little more complicated. Yeah. So with the transport protocol, there is an encrypted handshake that happens. Connections are established via some kind of cryptographic handshake, and once they're established, packets end up being encrypted, and they are encapsulated as frames. So in phase 1, we have peer authentication with some kind of encryption handshake, and the peer authentication part, the purpose of that is to establish some kind of secure communication channel by setting up some kind of encrypted authentication scheme or stream. And then you have the encryption handshake, which is to exchange temporary keys to set initial values for this secure session. And then phase 2 is essentially the base protocol handshake, and this is where we negotiate supported protocols, which I showed you in the distributed hash table diagram earlier. But what happens is, to create a secure connection, the initiator sends an authentication message to receiver. If you're familiar with message authentication codes, this is what it's doing. Receiver responds with an authentication response message, and it ends up setting up some kind of secure session. Then the initiator checks the receiver's response and establishes that secure session. And now they basically send the base protocol handshake, and they exchange what they support. So there's actually like a lot going on between where they share their platforms, right? They make the handshake, and then they finally say, okay, we're ready to communicate over our TCP connection. And either side can disconnect if that authentication fails or the protocol handshake just isn't appropriate, right? Like in a case where it isn't appropriate, that's where like the two Ethereum versions don't agree, or you're trying to use something that isn't supported. And if it fails, then the information must be removed from the node table. So for that user's personal node table, and as well to the distributed hash table. After a certain number of failures, it also gets updated. But due to the limited number of IPv4 spaces and common ISP addresses, this is actually pretty common. So I mean, no other action should end up occurring because whenever you try to make a handshake with another person in the network and there's no action that should end up occurring. Is there another class in here? I see. Oh, okay. Yeah. I guess I'll end there. We'll talk about more stuff in lab that's kind of related to it. If you have any questions, feel free to come up to me and ask.